Alright, let's talk about performance in computers. So we're using this PIC chip, which is, a very small, inexpensive microcontroller. You use it for, managing some embedded system. It's not designed to be a powerhouse. It's not something that you're going to, build a complex video game on or use for complex scientific calculations. It's basically, a little processor that can read, process, update outputs, and so on. So we don't normally think a whole lot about the speed of this PIC processor and the things that we ask it to do, taking in two numbers and adding them. We're flipping some switches in the simulator or on a proto board, and whether it can accomplish this in a few nanoseconds or a few milliseconds, it looks the same to us. We don't really see a whole lot of difference, but certainly if we were building, a computer to do large scientific calculations or try to do advanced rendering of graphics for a video game, right, we'd be very concerned with these little nuances in performance. So this is a bit of a theoretical topic for the processor we're working with, but let's talk about performance and pipelining. And one of the first ideas when people started using computers and realized they could calculate faster than people could and so on was, well, what if we get computers to work together? If one computer can do this in 10 seconds, maybe two computers together can do it in 5 seconds. And so we get this idea of, trying to parallelize tasks. And it's a great idea in theory, but in practice it doesn't work. So suppose you're trying to paint a room, and suppose working by yourself, so one person, is going to take 10 hours to totally paint the room. And I'll put this in seconds. This is 36,000 seconds. So what's involved in painting a room? Well, you got to put down drop cloths. You've got to, mix the paint. You've got to pour it into a pan. You've got to get a roller and put the roller in the pan and then run it along the walls and do touch-up work and do clean-up work, and you've got to keep refilling the pan and so on and so forth. And for one person to do this, it's very straightforward, but it takes a long time. And so maybe you get a friend and you think, we'll have two people and maybe we can do this in 5 hours, which is 18,000 seconds. And that probably works, especially if you have two rollers and two sets of drop cloths and two pans, and each person can be kind of doing their own thing. And so, I could work on these two walls and my friend could work on those two walls, and we don't really get in each other's way. And maybe we goof off some, or we stop and we talk and so on. So there might be a bit of a performance hit, but doubling the speed of the task kind of makes sense. But then if we get 10 people, can we paint the room in 1 hour or 3,600 seconds? Well, this is going to be a little less likely, especially if it's a small room, because 10 people moving around with 10 containers of paint and 10 rollers, trying not to, get in each other's way, step on each other's materials, drip paint on each other's head, it's probably not going to work so well. So let's look at this idea of speed up. And if we were to take the extreme, if we could pack 36,000 people into our room, could we paint the room in 1 second? Well, 36,000 people, no. So what happens here? Why doesn't this parallelization work? So let me propose a formula, and let me say that if you have n people, the task time is going to be 36,000 seconds divided by n. But there's going to be overhead, and the overhead gets worse the more people you add. So I'm going to say, just sort of randomly, 30n squared. This is our overhead. So there's a non-scientifically generated formula for how long it takes to paint the room if you have n people working on it. 36,000 divided by n, that's, dividing the 10-hour task into n pieces, but also adding a bit of overhead to that time because people have to, stop what they're doing to let somebody else go by, and, maybe you need to move a drop cloth that somebody else is standing on, and so on and so forth. So let's look at what this formula does for us for different values of n. So if we have one person, this looks like 36,000 and 30 seconds overhead. So 36,000 and 30 seconds. Now if you have two people, this looks like 18,000 plus 30 times 4, that's 120, so this is 18,120. Is that better than that? Yeah, this is just over 5 hours. The original time was a little over 10 hours. So 2 people, you're definitely getting a speed up. All right, what about 10 people? Well, 36,000 over 10 is going to be 3,600. And then 30 times n squared is going to be 100. That's going to add 3,000. So this is going to be 7,600 seconds. And notice what's happened here. We increased the number of resources by 5x, but our time got a little better than half of what it was. We didn't get a 5x reduction in the time. We got something closer to, half the time. And if we have 20 people, well, 36,000 divided by 20, that's going to be 1,800, but the overhead is going to be 30 times 400. Well, that's 12,000. So this is going to turn out to be 13,800. So when we add more resources, it ends up taking us longer to complete our task. All right, so this is a attempt at a pseudo real world example of where adding more resources doesn't necessarily get you more time. At some point, there's what you call a point of diminishing returns. And if we were to graph this out, we see something like this. And there's some sweet spot, some number of resources at which we get the best possible time. Before this, we're losing time because each resource has to do too much work. After this, we're losing time because the overhead is increasing and outweighing the effect of cutting the task into smaller pieces. So that's one thing to keep in mind, right? There's no system that we know of where you can just keep throwing more and more things at it and it just gets more and more efficient. The overhead starts to win out. All right, and this is somewhat related to something called Amdahl's law. So Gene Amdahl was a giant of computer science engineering, and this law is credited to him. And the idea is basically be careful what you optimize. So suppose that we have some procedure that we're trying to perform, and it can be broken into 3 pieces. So piece A, piece B, and piece C. And it takes a certain amount of time to do each of these, and so we can find a total amount of time. And so suppose the total amount of time it takes us is 41 minutes. And we want to speed up this process. So we look at these 3 pieces. Maybe this is some initialization, some main loop, and some concluding operations, or 3 chunks of code. And we dig into the code. We're gonna look later at how C gets compiled into assembly language and think about ways that we can improve the performance of this compiled code. So we can do things, and maybe we look at procedure A, and we discover, hey, we can double the speed of this if we spend enough time rewriting the code. We can double that speed. Well, that's pretty good, right? And we look at procedure B, and maybe we can triple the speed of that. And then we look at procedure C, and we get a very bright person to look at it, and they say, hey, I can make this code run 100 times faster. And you've only got enough money to pay somebody to optimize one of these sections of code. Which section would you like to optimize, A, B, or C? Well, the naive answer is, let's optimize C because we get 100x speed up, right? And that's way better than doing a 2x or a 3x. But it's not as simple as looking at how much you can optimize an individual piece of code. We also need to look at how much time we're spending in each of these pieces of code. So suppose in this 41 minutes, we spend a total of 10 minutes in part A, and 30 minutes in part B, and 1 minute in part C. So that's why we get 41 minutes. Now, if we were to apply these optimizations, a chunk of code A that takes 10 minutes, if we can double the speed, that's going to take 5 minutes. B takes 30 minutes. If we can improve the performance by 3x, this is going to take 10 minutes. And part C takes a minute. If we can improve that by 100x, that's going to take 0.01 minutes. So if we decide to improve procedure A, that's going to take us from 10 minutes down to 5 minutes. It's going to save us 5 minutes. We're going to end up spending a total of 36 minutes. If we improve procedure B, that's going to take 10 minutes off our total time. It's going to be 31 minutes. If we improve procedure C, that's going to take 1/100th of a minute off of our time. That's going to end up taking 40.99 minutes. So if we can only do one of these optimizations, which one should we do? We should optimize code B. But it's not the one that we get the biggest improvement on. So that's what Amdahl's law is saying, basically. It's saying that the overall performance increase that you can expect is dependent on how much of your total time is being spent in the thing you're trying to optimize. So when you run code profilers to see where you're spending time on, it's something we talk about in CSE 224. When we analyze an algorithm and we say, oh, this is the part we can speed up the most, that's not necessarily where we want to optimize. And this is tied in with the idea of how do we get a better performance out of a system. So let's take a look at the PIC processor, and let's do some calculations. So we have table 20-1, which shows all of our instructions, and one of the columns here is cycles. And cycles tells us roughly how much time it takes to execute this instruction. So most of our instructions take 1 cycle. If we look at the byte-oriented instructions, they're all pretty much 1 cycle. The ones that involve comparisons and possibly skipping or jumping take 2 or 3 cycles. These strange instructions that take 2 words, 32 bits, those are 2 cycles. But increment, add, clear, 1 cycle each. So what is 1 cycle? What does that mean? Well, if you take a look at the oscillator subsystem in the PIC processor, there's an internal oscillator which generates this 8 megahertz signal, and then it can go through, this is basically a counter, so like Engineering 250, a bunch of toggle flip-flops maybe, that divides this 8 megahertz signal either in half, a quarter, an eighth, a 16th, and so on. And we also have a special low quality, an RC generated signal, 31 kilohertz. So we are able to generate from this piece of our system an internal oscillator running at anywhere from 8 megahertz down to 31 kilohertz. And that's what goes into defining what a clock cycle is. But it's not quite that simple for reasons that we'll talk about in a minute. But one clock cycle, let's suppose we're running at 32 kilohertz. It's actually 31, but it's an approximate 31, and 32 divides out nicely. So we'll just approximate our clock speed at 32 kilohertz, and that's the speed we usually work at in the simulator. It's kind of the default clock rate. So 32 kilohertz is one clock cycle. It turns out that it takes 4 clock cycles to make what we call an instruction cycle. This clock inside the system has to tick 4 times in order to generate one instruction cycle. And so we get approximately 8,000 instruction cycles per second. So if we want to find out how long an instruction cycle takes, we could say 8,000 instruction cycles, and let's just write out 1,000,000 microseconds. And so we can flip this around. 1,000,000 microseconds gives us 8,000 instruction cycles, and we can cancel. So 1,000 over 8, that's 125 microseconds per instruction cycle. And that's the basic back of the envelope number we're going to use when thinking about how fast our code's going to run. An instruction cycle, approximately 125 microseconds. And these numbers that you see in this table, these are instruction cycles. They just call them cycles. So running with our 32 kilohertz clock, an add WF instruction takes 125 microseconds. A move F takes 125 microseconds. A move FF takes 2 cycles, that's 250 microseconds, or a quarter of a millisecond. So that's our basic calculation. So 1 instruction cycle, 4 clock cycles, and this frequency, this clock frequency, system clock frequency, determines how long one of these system clock cycles is. So basically take your system clock frequency, divide by 4, you get your instruction clock. So the fastest we can run with this built-in oscillator, 2 megahertz. 2 million instruction cycles per second, which means, we could do 2,000 increment instructions, 2 million increment instructions every second, which is pretty fast for a little single chip processor that costs a few bucks, right? Now it's not, in the gigahertz range. That's something like, an Intel processor would run at, but 2 million operations a second, that's pretty sweet. But we can do better. So this brings us to the topic of pipelining. So what is pipelining about? Well, pipelining is about the idea that if we only do one thing at a time, and if it's going to take us 125 microseconds to do an increment, it's going to take 125 microseconds. But suppose that while we're incrementing one file register, we could be doing something else at the same time. If each of those things takes 125 microseconds, but we can accomplish 2 of them in that time, we've effectively doubled the speed of our processor. Alright, so let me give you another pseudo real world example of how we can set up a pipeline. So, so suppose you're doing laundry, and let's say that you've got 4 steps to doing your laundry. The first is to wash your clothes. So you put them in a washing machine, and then you put them in a dryer, and then you fold them, and then you store them in your closet. And for simplicity, let's suppose it takes 1 hour, so 60 minutes. I don't think it takes most of us 60 minutes to put our clothes away, but for the sake of simplicity, let's suppose each of these stages takes 60 minutes. Alright, so you want to do 1 load of clothes. How long is it going to take you? 1, 2, 3, 4 hours. You wash them, you take them out, you dry them, you take them out, you fold them, you take them out, you store them. It takes a total of 4 hours. Now, if you want to do 2 loads, the not very clever way to do this is take your first load, put it in the wash, wait an hour, put it in the dryer, wait an hour, fold it, wait an hour, store it. When you're done with that, take your second load, put it in the wash, and then dry it, fold it, and store it. 2 loads, going to take you 8 hours. And if we continue with this, 5 loads is going to take 20 hours. But of course, if you have enough resources, what can you do? Well, you put your first load in, the wash, and you wait an hour. And there's nothing you can do during that hour to help with your laundry. You're just waiting for the wash to finish. After an hour, you take that first load and you put it in the dryer, but at the same time, you put your second load into the washer. You got parallelism. Alright, after an hour, this load is dry. You go ahead and you start folding this, but you also take load 2 from the wash, put it in the dryer, and you take load 3 and you start that in the wash. Alright, an hour later you finished folding your clothes. Here's where you need more resources. You get a friend and you convince them to store your clothes for you. So your friend, the next hour, takes load 1, starts putting it into your dresser. You take load 2 from the dryer and start folding it. Load 3 goes from the washer to the dryer, and load 4 goes into the wash. Now it's been 4 hours and you haven't finished any laundry yet. But the next hour, what's going to happen? Hour 5, load 1 is done. Load 2 is going to get put away. Load 3 is going to get folded. Load 4 is going to get dried. Load 5 starts in the wash. And an hour later, load 2 is done. And then the next hour, you take load 3, start putting it away. Load 4 starts getting folded. Load 5 goes in the dryer. And load 6 goes into the wash. And an hour later, load 3 is done. So what's happening? Nothing happened for the first few hours. But then you finish the first load. An hour later, you finish the second. An hour later, you finish the third. If you keep this up, it looks like 1 load takes 1 hour. So we've sped up the effective amount of work we can do in a certain amount of time by using this process called pipelining. So this is what we do inside computers. We try to arrange our process of fetch, decode, execute, right? The 3 steps we do for executing an instruction. We try to do that in pieces that allow us to pipeline the process. And so the reality is, on the PIC processor, we said that one instruction cycle takes 4 clock cycles. That's not true. It actually takes 8. But there's a 2-stage pipeline. And so in general, we have 2 instructions being worked on simultaneously, and we have this pipeline set up. And so we have something like a fetch, decode, and an execute. And while we're executing one instruction, we're fetching and decoding the previous instruction. And once our pipeline is full, we effectively cut the throughput. We double the throughput. We cut the effective time in half. So instead of actually taking the 8 instruction cycles, the 8 clock cycles for one instruction, it looks like we only need 4 clock cycles. And so this is a simplification of what's actually happening. But it's the simplification we work with in most cases. This is the reason why when we have something like a branch statement, it takes 2 cycles. Well, why is that? It's not because a branch is fundamentally more complex. It's because when we make a branch, we clear out the pipeline. Right? So what happens in this laundry pipeline? We're going along happily. We've got, one load finishing every hour. And all of a sudden we realize, hey, we're doing the wrong laundry. This isn't my laundry. This is my roommate's laundry that I'm doing. And we don't feel like, spending time on our roommate's laundry. So what do? We take the stuff that we're currently storing, and we take the stuff that's currently being folded and dried and washed, and we, dump it on our roommate's bed or something. We wouldn't do that, but and our pipeline is empty again. And now we take our load and we put it in the wash, but we're just sitting there, watching TV, waiting for the wash to finish so we can move it over here, and we're back to this state where it's going to take 4 hours for load 6 to come out of our pipeline. So that's called a pipeline stall. Okay, how does this happen inside a microcomputer? Well, we have a set of instructions, and reading an instruction out of memory takes a certain amount of time. We have to take the program counter, send it to the address of our memory unit. We have to send a signal saying read, wait for the circuitry to respond, send us back the information, then we have to start decoding it. And say, oh, this is an increment instruction, here's where we're trying to increment, and so on. And then we actually do the instruction. So we can fetch this first instruction, and then when we begin to execute it, we also at the same time start fetching the second instruction. So it took 2 of these chunks of time, 4 clock cycles, to do our fetch and then to do our execute. But while we start executing this, we're at the same time fetching the third instruction. And then when we're executing that, we're fetching the 4th instruction. And if we do this right, once our pipeline is full, it looks like every one of these instruction cycles, we complete a new instruction. So here's what this looks like on the PIC. Q1, that's our system clock. That's the internal oscillator. 8 kilohertz, 32 kilohertz, 8 megahertz. That's that oscillator coming out of our oscillator control block. Here's the 4 pieces that we break that into, those 4 clock cycles that we need for one instruction cycle. So this, from one dashed line to another, that's an instruction cycle. So in this first set of 4 ticks, we're fetching instruction at, particular program counter, and we're executing the instruction that we fetched previously, the one that was 2 spots earlier. In the next set of 4 clock cycles, we're executing the instruction that we fetched over here, and we're fetching the instruction that comes next. In the next chunk of time, we're executing the instruction at PC plus 2, and we're fetching the instruction at PC plus 4. So each time the execute finishes, we've finished an instruction, and the effect is it looks like we're finishing an instruction every 4 clock cycles. So here's another way to look at it. We fetch the first instruction. We execute it after that while we're fetching instruction 2. We execute 2 while we fetch 3. We execute 3 while we fetch 4. But suppose that step 3 was a branch instruction. Well, we fetch the branch instruction here. We don't know that it's a branch until we do the execute. And while we're working on executing the branch, we're pre-fetching this 4th instruction. And this 4th instruction, is the one that comes right after the branch, but that's not the instruction we want to execute next. Because this branch says, hey, we should go down to some other location, sub 1, and execute stuff from there. So after we finish executing the branch right here, we realize, oh, this instruction that we just finished fetching, that's not the right instruction. We have to spend our next clock cycle fetching the correct instruction, and there's nothing we can do to execute at that point. So this is a pipeline stall. Sometimes we say we're flushing the pipeline. And then after we fetch the correct instruction, we can go ahead and execute it. So we lose our parallelism because while we're fetching sub 1, there's not an instruction we can be executing in parallel. Right? Because the instruction we fetched in cycle 3 was not the correct one. So that's a pipeline stall. And this is why branches take twice as long. So an unconditional branch always takes 2 cycles. Conditional branches can take 1 or 2. What's the difference? Well, if you branch, it takes 2. If you don't branch, it takes 1. Because if this is a conditional branch, right, say this is a branch of 0, so we're figuring out should we branch, and we're fetching instruction 4. If it turns out we should not branch, we've already fetched the correct instruction here, we can execute it right here. So there's no stall. So the mantra in computer architecture is that pipeline stalls kill your performance, and pipeline stalls are caused by branches. So if you can avoid branching, you can keep up the full pipeline and get better performance. And on a more sophisticated processor, we might see a pipeline that's several stages deep. Not just 2 stages like on the PIC processor, but we might see several stages to the pipeline. And so imagine that you can take your system, the time it takes to execute an instruction, cut that by like 7 or 8 or 10, right? You get a much, much better throughput, better performance. But as soon as you get to a branch, all bets are off. You have to wait until that pipeline gets filled up. And the longer the pipeline, the worse the penalty of a stall. The longer it takes to refill the pipeline. So it'd be great if we could avoid branches. Well, you can't really do that, right? You've got a branch in code. But if we could predict ahead of time whether or not a branch is going to be taken, we can effectively avoid the effect of these pipeline stalls. So imagine that when we saw this branch, we could somehow, before we get to the execute phase while we're fetching it, we could at least recognize, hey, this is saying that our next instruction is going to come from here, so that down here when we do our fetch, we're actually fetching the correct instruction. Then we avoid this stall. Well, that's not too hard to do with a branch statement because, it's just a certain opcode. But conditional branches, suppose we have a branch of 0 to some other section of code. Well, until we get to this instruction and can see what the status bit looks like, we don't know if this branch is going to happen or not. So, and if our pipeline is very full, it might be several stages of execution before we get to the point where we can determine, is this bit 0? If we're executing 7 instructions in a row, and this branch depends on the previous instruction, we don't know until right before this instruction executes whether or not we're going to branch. So this brings in the idea of branch prediction. And branch prediction means you put a little oracle inside your CPU, that tries to predict the future. And when it comes up to a conditional branch, it tries to guess without knowing what the actual instructions are going to do. It just tries to guess, am I going to branch or not? And it does this by basically looking at what's happened in the past. So in later CS courses, Engineering 250, courses like that, sometimes we talk about, as an example of a state machine, a weather predictor. Something that predicts tomorrow's weather based on today's weather. Well, that's basically a branch prediction model. So you can go back and look at your 250 notes maybe and find that in there. But this is something that we do, and it's one of the many tricks we use in modern processors to try to keep the speed as high as possible. And we do that by trying to keep the pipeline as full as possible by basically trying to predict the future. And it's a worthwhile thing to be able to do. All right, so that's just a little bit about performance and speed ups, parallelism, pipelining. The good news is none of this really affects us on kind of a day-to-day basis when we're working with this processor. We basically, write our code as reliably as possible. We don't generally worry in this course about performance. But we do sometimes need to know how long something's going to take. We want to generate a delay loop, for example. We want to wait 3 seconds before we do something. We do that by knowing how long instructions take to execute. But for the most part, we just kind of stick with the rule of, take your system clock frequency, divide by 4. That's your instruction clock frequency. And this number tells you how many instruction cycles it takes. And generally it's 1. Calls, go-tos, move-ff, those take 2. Conditional branches that are taken, or unconditional branches, take 2. But for the most part, it's generally one instruction cycle. So we can do rough calculations. So there'll be some homework problems to play around with, calculating how long things take and so on. All right, thanks.